The content in this presentation is covered on pages 201 through 206 of your textbook, and it's meant to help you achieve learning objective number 34, which is to name and describe the factors that affect air pressure at Earth's surface as well as aloft. Be sure to skim these pages before watching the video and to read the chapter carefully before attempting the online quizzes. What's the importance of atmospheric pressure and its daily variations? Remember that variations in air pressure cause the wind to blow, which in turn causes changes in temperature and humidity. So differences in air pressure create global winds that become organized into the systems that bring weather. Therefore, the National Weather Service closely monitors daily changes in air pressure. Although pressure changes with altitude are important, meteorologists are also interested in the horizontal pressure differences that occur around the globe. So horizontal pressure differences from place to place tend to be relatively small. Extreme readings are rarely more than 30 millibars, or 1 inch of mercury above average sea level pressure, or 60 millibars below average sea level pressure. Occasionally, the barometric pressure measured in severe storms, such as hurricanes, is lower. But these small differences in air pressure can be sufficient to generate violent winds. Four primary factors contribute to changes in air pressure. Those are altitude, temperature, humidity, and the movement of air masses from one location to another. Just as you experience a decrease in water pressure as you rise from the bottom of the pool, there's a decrease in the air pressure as you ascend from the ground surface into the atmosphere. What you're actually experiencing is a change in the density of the air. At sea level, a column of air weighs 14.7 pounds per square inch and therefore exerts that amount of pressure. As we ascend through the atmosphere, we find that the air becomes less dense because of the continual decrease in the amount of air above. So there's a corresponding decrease in pressure with every increase in altitude. Because density decreases with altitude, the term thin air is normally associated with mountainous regions. Remember that the rate at which pressure decreases with altitude is not constant. The rate of decrease is much greater near the Earth's surface, where the pressure is high, than it is aloft, where the pressure is low. A model of the U.S. standard atmosphere, shown in this figure, depicts the idealized vertical distribution of atmospheric pressure at various altitudes. Remember that near the surface, air pressure decreases by about 10 millibars for every 100-meter increase in elevation, or about an inch of mercury for every 1,000-foot rise in elevation. Further, atmospheric pressure falls by approximately 1/2 for each 5.6 kilometer increase in altitude. So at 5.6 kilometers, the pressure is 500 millibars, about 1/2 of the sea level value. At 11.2 kilometers, if we double that again, we're down to about 250 millibars, or 1/4 the sea level value. And that decrease is systematic and continues on up the column. So at the altitude at which commercial jets fly, 10 to 12 kilometers, the air exerts a pressure equal to only 1/4 that we would experience at sea level. Because temperature is a measure of the average molecular motion, or the kinetic energy of a substance, cold air is composed of comparatively slow-moving gas molecules that are packed very closely together. For this reason, cold Dense air masses are associated with high surface pressures, and are labeled with H's, blue H's, highs on weather maps. By contrast, during the summer, large areas of the American Southwest experience extremely high temperatures, accompanied by low surface pressures labeled low or red L's on the weather map. So all else being equal, a cold air column is associated with high surface pressure, and a warm air column is associated with low surface pressure. These pressure differences, in turn, generate a force called the pressure gradient force that causes the air to flow. Air flows from areas of high pressure to areas of low pressure. And this figure shows you another important difference between cold and warm air. Air pressure drops more rapidly with increasing altitude in a column of cold air, because it's dense, than it does in a column of warm air, which is less dense. If you assume that both columns of air exert the same surface pressure, and that differences in the spacing of air molecules represent differences in density, air pressure decreases more rapidly with altitude in a cold air column because the molecules are closely packed together. So if we could move up the imaginary column of cold air, we would quickly pass through the dense molecules near the surface. But in a warmer, less dense column, the pressure drops more slowly because we would pass through fewer air molecules in the same vertical distance. Because of that difference, you can conclude that any given altitude above the surface, there's more air molecules in a warm column than there are in a cold column. So as long as the elevation is the same, we're going to have higher pressure in a warm column than we would in a cold column, even though these surface pressures are the same. If we look at the line drawn halfway up the two columns shown here, we can see that there are more air molecules above the line in the warm air column than there are in the cold column. And as a result, above the surface, warm air tends to exhibit a higher pressure than cold air, opposite of what we see on the ground. Note that this is just the opposite, right, of the surface. Cold air usually exerts higher pressure than warm air at the surface. But when we get to the upper condition, remember this figure with the line drawn halfway up the warm and the cold columns. So the warm has more molecules above it, above the white line, so the warm column has a higher pressure. The cold column has fewer molecules above that white line. So when we talk about above the surface, aloft, it has lower pressure. You're hearing my daughter in the background there. Although less important than temperature, the amount of water vapor contained in a volume of air influences its density. Contrary to popular perception, water vapor reduces the density of air, so the air may feel heavy on humid days, but it really isn't. You can easily verify that fact for yourself when you look at a periodic table of the elements. Notice that the molecular weights of nitrogen, right, most of the atmosphere, and oxygen, the second most abundant gas in the atmosphere, are both greater than that of water vapor. So if we add two H's and an O together, the three gases, nitrogen, oxygen, and water, have relative masses of 28, 38, and 18 grams respectively. So the water actually, if a certain percentage of that air column is water vapor, it should actually make the column lighter, lower in pressure. In a volume of air, the molecules of these gases are intermixed, and each takes up roughly the same amount of space. As the water content of an air mass increases, lighter water vapor molecules are taking the place of the heavier molecules. Therefore, humid air is less dense than dry air. Nevertheless, even very humid air is only about 2% less dense than dry air at the same temperature. So to summarize this, temperature differences add to a lesser extent moisture content causes horizontal pressure differences, producing a force that causes air to flow from areas of high pressure to areas of low pressure. In general, cold, dry air produces higher surface pressures than warm, humid air. Further, a warm, dry air mass exhibits higher surface pressure than an equally warm but humid air mass. So when we get to conditions aloft, that situation is reversed. Warm air aloft tends to exhibit a higher pressure than cold air at the same height above the surface. The movement of air causes changes in air pressure. For example, in situations where there is a net flow of air into a region, air accumulates. That phenomenon, which is called convergence, causes air to be squeezed into a smaller space, and that results in a more massive air column exerting more pressure at the surface. By contrast, in regions where there's a net outflow of air, a situation referred to as divergence, the surface pressure drops. We'll return to the important mechanisms of convergence and divergence in the next video. Use the course content provided on the Canvas site as well as outside internet sources, if you can find trustworthy ones, to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape for the test. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.